Designing of energy-efficient rotary steam coil air preheater, SCAF, for fossil-fueled thermal power plant. Abstract: steam coil air preheaters, SCAF, are found in most fossil-fueled utility and large industrial power plants. Their primary function is to preheat combustion air before it enters rotary regenerative air preheater or recuperative type air preheater. SCAF provides corrosion protection for the air preheater and maintains its cold end average temperature above acid dew point temperature during cold stringent weather condition. Most units use vertical, fixed fin tube coils embedded in the ductwork connection of the discharge side of combustion air source, forced draft fans, and the cold end inlet of air preheater. This equipment can also have an additional purpose of preheating the combustion air during unit startup by increasing the ambient air temperature up to a desirable temperature to reduce fuel oil consumption, thus aiding operators to take pulverizer into service early. Along with the advantages of this static bulky heat exchanger, there lays a hidden disadvantage which impacts the auxiliary power consumption during normal unit operation at normal ambient conditions. As it is present in the discharge of forced draft fan, a considerable amount of pressure drop occurs across the coils, which leads to an increase of forced draft fan loading, thus leading to an increase in auxiliary power consumption even in normal weather conditions. Without hampering the normal functionality of the SCAF system, an innovative approach has been taken and described in this paper through redesigning of a static SCAF system into a rotary SCAF system. Keywords: steam coil air preheater, rotary equipment, auxiliary power, retrofit, innovation, modification, energy efficiency, SCAF. Introduction. Heating and cooling systems technology is one of the most important areas of mechanical engineering. Wherever heating and cooling of fluids is incorporated in a system, we will find a heat exchanger. Heat exchangers have wide industrial applications and it is practically inexhaustible. In our basic study of heat transfer equipment in modern power stations, we often come across the term steam coil air preheater, SCAF, which is a heat exchanger used to heat atmospheric air to the required process temperature by means of superheated steam in thermal power industry. Steam flow inside the tube while air passes over the fin tubes. It is generally used for heating process air or combustion air. SCAF has extensive uses in all high-capacity boilers and recovery boilers. Steam coil preheater is used to heat inlet air to air preheater type, APH, in order to raise the cold end temperature, thus preventing acid dew point corrosion. This type of equipment is normally incorporated into design of a boiler unit for low-load operation, and it can be used during unit startup operation also. It has fin tubes which increases heat exchange surface area. It is generally located in the duct between the forced draft fan and the air preheater. Figure 1 and Figure 2 shows the arrangement of the fins in the tubes of SCAF. Introduction to air preheater, APH, and discussion on cold end corrosion. Air preheater is a heat recovery equipment, which improves the efficiency of boiler and also reduces the fuel consumption to extent of nearly 5% depending on duty. Figure 3 shows the rotary regenerative air preheater and its major components and flow path of air and flue gas through it. In air preheater, the combustion air is preheated before admitting the air to combustion zone or furnace. The air preheating can be heated up to 300 degrees C depending on type of combustion equipment. Since the heat is extracted from flue gas, the temperature of the flue gas can fall below the acid dew point temperature, which generally ranges between 90 degrees C to 110 degrees C for Indian coals. As the ambient temperature falls down, there is possibility that overall bulk mean temperature of the gas may fall below 110 degrees C. SO3 and H2O present in the flue gas start to react with each other at such a lower temperature. Figure 4 shows the values of sulfuric acid dew points as a function of sulfite content in the flue gas and moisture. To increase the efficiency of the boiler, SCAF is introduced before air preheater. In SCAF, the low temperature ambient air is heated by low pressure steam to avoid cold end corrosion. Apart from that, preheating combustion air by usage of SCAF during unit light up aids in reduction of fuel oil consumption by enabling operators to take pulverizers early. but during normal ambient temperature conditions and full load operation of thermal units, Scaf loses its usefulness and becomes a bulky burden as an auxiliary. This system imposes a resistance on the forced draft fans by the constant pressure drop across it. In this technical paper we will discuss the methodology of converting the static auxiliary into a dynamic rotary equipment through which we can reduce the resistance in the flow path of combustion air, thus extracting benefit from the SCAF system even during normal ambient conditions and full load unit operation. Introduction to the implementation. Site. The retrofitting of the SCAF system and implementation has been carried out in Sason Ultra Mega Power Plant, SUMP, which is a subsidiary of Reliance Anil Dhirubhai Ambani Group located in Singrauli district of Madhya Pradesh. The plant capacity is 3,960 MW, 6x 660 MW, based on supercritical technology having the best-in-class efficiency. It provides power at most competitive tariff in the country to 14 DISCOMs in 7 states. Sason Power Limited, SPL, also has a mining production capacity of nearly 20 million metric ton per annum, MTPA, which is made possible by the state-of-art mining equipment and largest size of heavy earth-moving machinery, HEM. SPL is one of the largest integrated thermal power plant with captive coal mines at single location. SPL is operating at full capacity on continuous basis since commissioning, setting, and raising benchmarks for the power industry every day. The plant has achieved numerous awards and accolades in all areas of operations and efficiency. On the path of inclusive growth, it is making a positive impact on the life of surrounding community by way of education, healthcare, and training for skill development. Design meteorological details. The elevation of power plant is 275 to 320 meter above sea level with design ambient temperature, dry bulb temperature, of 32 AA degree C and the extreme atmospheric temperature ranges between maximum of 42 AA degree C, minimum 8.1 AA degree C. Boiler. The boiler at SPL is a supercritical, variable pressure operation, spiral tube once through, single furnace, single reheat, tangential firing, balanced draft, semi-outdoor arrangement, 2-pass type manufactured by Shanghai Boiler Works Co. Ltd. Turbine. The turbine model in SPL is N660224.2/566/566 which is a supercritical, tandem compound, combined high pressure, HP, and intermediate pressure, IP, to low pressure, LP, turbine double flow, intermediate reheat, condensing type turbine manufactured by Shanghai Electric Power Generation Equipment Co. Ltd. Table 1 shows the details of the forced draft fan operating parameters installed at SPL and manufactured by Shanghai Boiler Works Co. Ltd. Internal diameter of the fan 2818 mm. Diameter of the impeller hub 1412 mm. Stage number 1. Number of blades per stage 16. Blade material HF1. Screwed connection between the blade and blade shaft. Impeller adjustment range -30 AA degree plus 20 AA degree. Scaf design parameters and operational usage details. Scaf, steam coil air preheater, is equipment fitted between forced draft fans and air preheater to avoid the acid dew point condensation which occurs at the flue gas side in the air preheater due to the low temperature of the atmospheric air as stated earlier in the paper. The design parameters of Scaf at SPL are as follows. Number of Scaf assembly, 02. Number of coils in one assembly, 04. Number of tubes, 42 in one coil. Inlet header size, 150 mm. Outlet header size, 50 mm. Scaf weight, 1.2 mt. Material of construction, tubes and other associated systems are made up of carbon steel having thermal conductivity around 45 to 50 Watt per meter Kelvin, SA210 grade. Operational details of Scaf system. The operating pressure of the steam is taken nearly 8 to 12 bar, depending upon the steam pressure available in auxiliary PRDS, pressure reducing to superheating steam, station and temperature is taken with a minimal amount of superheat from saturation temperature at that corresponding pressure. Forced draft fan deliver the air at ambient temperature and at pressure of 150 to 220 mmWc, millimeter of water column, draft pressure. Generally, 20 to 25 mmWc pressure drop occurs in the Scaf due to its complex geometry. Scaf is taken into service when ambient temperature falls and reduces the flue gas outlet temperature of APH. Scaf is also taken into service during unit startup and low load operation. Generally, in unit startup till synchronization oil guns are kept in service, but due to various changes in material composition of boiler and change in operational philosophy nowadays mill is taken in service prior unit synchronization. But there are some prerequisites that are to be followed prior taking pulverizer in service. One such condition is that the secondary air or combustion air temperature at APH outlet should be greater than 160 degrees C. Now, since ambient air temperature at 30 degrees C passing through APH and gathering heat from the low temperature flue gas at unit startup will require more time to get heated up to 160 degrees C, by using Scap the same activity becomes less time taking. With the initiation of Scaf charging process we try to preheat the combustion air temperature from ambient temperature to at least 6065 degrees C prior sending it to APH for heat gain. This in turn reduces oil consumption. After unit synchronization the steam source to Scaf is isolated. Scaf system arrangement, Figure 5 shows the single line diagram of the Scaf system arrangement at SPL prior modification. Concept of the modification and planning. There were many ideas which were pondered over to reduce auxiliary power consumption associated with the Scaf system. Firstly, we thought of eliminating the Scaf permanently from the system, but it would have left no option to help during times of cold and corrosion prevention. The second idea was to make an investment on erecting a bypass duct with additional path for air to the Scaf system and to erect additional dampers for isolation during non-usage period. But it would be bulky and would require space. Lastly, it was decided to turn the static Scaf into a rotary Scaf so that when not in use it remains parallel to the airflow path without causing any restriction in air path, and thus the system resistance will automatically get eliminated without sacrificing the benefits of Scaf to prevent cold and corrosion during peak winters or start UPS. In order to rotate such a bulky static system we have to first check for the points which upholds the weight of the tube banks, which as shown in figure 6 was the steam carrying inlet header. It acted both as the source of steam supply as well as the support to the tube banks. So in order to rotate the tube banks supported by the inlet steam header we have to transfer the weight of the tube banks to another section or system, which in our case was a channel, which would be discussed later, and then provide the steam supply through a different path as shown in figure 16. Based on this concept we chalked out the in-house methodology of erection, and it was a challenge for us to carry on with this modification at the lowest possible cost. Static Scaf was thus modified into a rotary Scaf, just like an operating butterfly valve, which can be rotated by 90 degree after unit achieves full load or when its requirement ceases. Man, machine, and material were expedited, and a step-by-step erection procedure has been explained in this paper. Step-by-step procedure for erection of a rotary Scaf. The procedure and methodology followed for the erection of the rotary Scaf are understated. OL. Removal and relocation of steam inlet header. It was required due to space constraint for erection of the structure and for hanging the coil banks of Scaf. It was done in order to erect the structure for Scaf with the help of channel of dimension 300 x 125 mm of length 4500 mm and of height 600 mm. Erection of channel over the Scafframe for support of Scaf coils. Scaf is located at the discharge of forced draft fan duct, and each forced draft fan consists of one Scaf system, and each Scaf system consists of 4 coil banks, and the total weight of all the 4 coil banks is 1,190 kilograms. According to the load of coil, it was decided to use a channel of 300 x 125 mm. At the top of the 4,200 mm wide duct of forced draft fan, a channel of length 4,500 mm was taken, and to support the channel from the side the same dimension channel was used of size 600 mm, which was welded with the horizontal channel and at the side of the duct to provide proper strengthening of the channel. Fabrication and modification of forced draft fan outlet duct. Within Scafframe in the previous SCAPH system, the center of inlet header was welded with the top of the forced draft fan duct, and minimum clearance was provided at outlet header discharge piping for thermal expansion of coils. The outer diameter of inlet header was 150 mm, so to rotate the Scap the duct height was to be increased from the center of the inlet header. The duct height was made to be 95 mm from the center of the inlet header. At the bottom of the duct, the discharge piping of outlet header, the clearance was increased. Pipe support provided from top to bottom frame of Scaf instead of box support. At previous condition there was a box channel which was provided, total 3 in numbers, for the support of the duct and locking of the coils, but it created hindrance in rotation of the coil at the time of trial of Scaf rotation, so we replaced the box channel with the pipe support of diameter 141A 10 mm and of length 6000 mm. Arrangement of stuffing box for air side sealing at both end for steam inlet and outlet line in each bank of coil. As the system was converted from static to rotary, there must be some clearances that had to be provided for rotating the coil banks and to resist the air leakage from these clearances. We were bound to provide a proper air sealing system from inlet and outlet steam header of Scaf. At inlet and outlet header we provided a stuffing box, to eliminate the air leakages and for smooth rotation of the coil banks. Extension and modification of steam inlet line length. After extension of top duct height, the inlet steam pipeline attached to the inlet header got short in length, so to provide the passage of steam to the inlet header, we provided a spool piece, which was welded with the inlet header steam line flange, of diameter 89 mm and of length 300 mm. In that spool piece at 90°A degree, a steam pipeline with flange was provided, which was then bolted with the main steam inlet header. Scaf coil bank loading and rotating arrangement. The individual weight of coil bank is 298 kg, which was acting vertically downward, and the bearing should be capable to bear this axial loading. Therefore, thrust ball bearing was suitable for loading and rotating purpose. For loading of Scaf coils, a hole of diameter of 110 mm was made in the channel to insert the shaft, which was to be loaded on the thrust ball bearing along with bearing base plate, which finally takes the load of coil with the help of tie rod, which was welded with the spool piece. Provision for alignment of Scaf coils was also done, and it was done with the help of adjusting nut screwed to the tie rod and base plate kept on the channel. Handle provision and locking arrangement of Scaf coil bank. For ease of rotation of Scaf coils in operating condition, a handle was provided, for rotating Scaf coil, which was welded with tie rod, and to avoid reverse rotation of coils we have provided a locking system to lock the handle after rotation. Flexible hose connection with inlet and outlet header. To reduce the effort to rotate the Scaf coil inlet and outlet connecting pipes were replaced with flexible SS hose pipes. Timeline and cost of the modification. During planned shutdown of the units at SPL, separate workforce was allocated for this project, and the completion was successfully executed within 6 days of the overhauling, including the time of material expedition, material lifting, erection and final completion of the project activity. The whole cost involved in this design implementation for both the SCAPHs was approximately INR 1.50 lakhs only. Cost-benefit analysis. The key driving force of any engineering design is the cost involved in executing it. If the cost involved or the payback time of the project is huge, then the sustainability of the project becomes questionable. Moreover, the project site is selling power across India at the cheapest price, so this innovative engineering design and modification had to be carried out at the lowest cost possible. The benefits envisaged from the implemented modification are tabulated in Table 2. At 670 MW load, same coal flow. and same secondary airflow. The forced draft fan A and B current cumulatively decreased by nearly 5.88 amperes, which amounts to a saving of 46.2 kWh for the 3.3 kV drive at a power factor of nearly 0.9 at site. Considering the average electricity tariff in India to be INR 3.50 per kilowatt-hour, then the amount for the electricity saved can be calculated to be nearly INR 14.16 lakh per annum. The payback period will be very minuscule, and it can be calculated by dividing the project cost by the benefit amount derived, which evaluates to less than 2 months. This profit is derived by pumping more electrical power, called NESO, into the grid for the same amount of generation. Conclusion. Through this pioneering implementation of rotary Scap, the units are running healthy and there are no issues from the operational side since its inception. Maintenance post-modification is also nil. During unit light-up post-tripping we take the rotary modified Scaf into service, and post-unit synchronization we rotate the Scaf by 90 degrees parallel to airflow path to nullify the pressure drop across it. This modification has reduced the auxiliary power consumption through decrease in forced draft fan loading. This redesigning of Scap is first of its kind in India and abroad and has been in successful operation ever since the in-house retrofitting at SPL. The re-engineered rotary Scap provides measurable and acceptable returns on investments and serves all its normal functionality, as well as it has been a contributor to efficient fossil-fueled power generation. We have brought up a new concept of this often forgotten plant auxiliary to retain its value both on and off its operation.